Hey everyone, welcome back to my channel. Today we're going to be working on problem number 1022, sum of root to leaf binary trees. Binary numbers. Now this is, as you guys can see, I have worked on this problem, but I opened it up. I worked on this back in 2021, but I got it wrong. And I haven't given it this knack at it since then. But to do this problem, what I'm going to try to do is I'm going to try to get this right, and hopefully the approach and algorithm I try to write out this time is correct. Now, most of the times on this channel, I work on problems that I have never worked on before, but if I do, I will like to explicitly state them and try to do them again without actually trying to submit them as a right submission. So let me reset this code to its original form, and let's go over the problem. So you are given the root of a binary tree where each node has a value of 0 or 1. Each root to leaf path represents a binary number starting with the most significant bit. For example, if the path is 0, 1, 1, 0, 1, then this could represent 0, 1, 1, 0, 1 in binary, which is 13. For all the leaves in the tree, consider the numbers represented by the path from the root to that leaf. Return the sum of these numbers. The test cases are generated so that the answer fits a 32-bit integer. It should be 32-bit integer. So the input is root, which you guys can see, it's all binary. So from root to leaf, it goes 1, 0, 0, then 1, 0, 1, then 1, 1, 1, and then 1, 1, 0. So what we want to do is create this type of layout in here, and then in the end, we want to add up all the numbers from binary that equal to the actual numbers. Let's take a look at the constraints. The number of nodes in the tree is range from 1 to 1000. Node.val is a 0 or 1. So there can never be any other values. So let's go over the actual steps in the interview. So the first step is to read the problem, read and understand the problem. And we have done that. The next step is to the algorithm. So let's think of the algorithm for this. For this, we can actually use pre-order traversal. So we go from root to left and then to right. But as we traverse down, we append each value. So the values are int val, right? So it's an integer. And what we want to do is we can actually use like a string builder to append each value from the string. Okay, there is a way to do it through the integer themselves, but I'm not sure exactly what the API is at the moment. So because we know that the range is not greater than 1000, we shouldn't have to worry about converting the string back to an integer. So what we would do is once we go down the tree in pre-order traversal, we would get 1, 0, 0, and then every time we backtrack, we remove from the string builder, and then we add the next value to the string builder. And then once we get to the leaf node, we add the values from the string builder into a list. And then in the end, we just traverse the list. So the algorithm is pretty straightforward. I don't think I need to write it down, but let's go over the runtime of this. So the runtime of this is of n because we traverse every single value, and the space time for this is going to be so we create a string builder every time. So the string builder will be of n, and then the string builder for every single iteration we're also adding, or so for every single path we're adding everything to a list. So it'll be of n plus of m, which boils down to of n. So if that seems okay, what we can do is continue with this approach. And so let's start if root equals null, return 0. Otherwise, we can call a algorithm called pre-order. And in here we pass in the root, and then let's call string builder sb equals new string builder. And then in here we pass in sb, and then we also need a list. So we need a list of string list equals new array list, and then we pass in the empty list. So let's use this. And we need to pass in the tree node root. And finally, we need to pass in the list. So for in order traversal, first we check if root equals null. We can just return. Otherwise, what we want to do is sb.append integer string.value of root.val, and pre-order, we call pre-order, and then we pass in root.left, sb, and then we pass in list, and then we call pre-order again, but this time we call in root.right. So the way this would behave is it would append to the string, append to the string, append to the string, then come here return. But now, once it backtracks, we remove from the string with so sb dot delete char at sb dot length -1. Also, before we even do that, if root.left equals null and root.right equals null, then what we do is we add list.add sb.to string. And then we come here if the final value is a leaf node, only we add it to the list, then we move back, then we come here, then we check, we come here, then we return, then we check is the root.left null and root.right equals null, then we add to the list. Otherwise we just backtrack, otherwise we delete from here, then we come here, then we backtrack again, and then every time we backtrack we perform this operation. In the end we have a list of strings that looks like this. And what we want to do is we want to add this to the sum, so you can have int sum equals 0, and for string s and list, what we can do is we can int char des value equals integer dot parse int, and then we pass in s, and then we put in 2, and we just do sum plus equals per des val, and then in the end we just return sum. So the SB will look like root.val. Okay, so SB will look something like this that we see on the screen, 100, and then we convert that into a decimal by using this syntax right here. And then we just add that to the sum. So it'll be 4 plus 5 plus 6 plus 7. Okay, so let me just make sure this pre-order is okay. We have root, SB, and then list. We append, and then we go left again, then return back to this root node. Then we go to the right using this line of code that's also null, then we return back, then we check if root.left equals null and root.right equals null, then we add this to the list, and then we delete, and then we backtrack, and then we go backtrack, then we go to here, then in here we go back if root equals, then we add 1 sb.append. Then we go to its left, then we return, then we go to its right, and then we return, then we check alright, and then just like that, we go through the entire loop. So let's try to run this. Okay, so this works, it's run. Okay, let's try to submit this. Okay, great. So the runtime was 3 milliseconds faster than 36.19. I think we did pretty good here, but let me know if you thought that there were any ways I could have improved. Thank you and bye.